Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chatterjee, and welcome back to my channel. For my non-civil engineer viewers joining us, please feel free to follow along by simply treating the technical terms as numbers and applying the process to your own DIY Excel projects. In my last video series, I explained the theoretical aspect of designing a doubly reinforced beam for bending stress, in detail, using a PowerPoint presentation. Now, I'm excited to introduce you to the application of those formulas that I explained in my video titled, Each and Every Steps for Doubly Reinforced Beam Design. Part-01 IS-456. This is the continuation of Part 1, and the title of this video is Bending Stress in Doubly Reinforced Beam IS-456, Part-02, Excel Presentation. This is the second installment of the series. If you're new here, I strongly encourage you to first check out Part 1 of the series. Additionally, my IS-456 singly reinforced beam design, bending moment, shear force and deflection limits and checks in Excel, series, Parts 1 through 7, will help you build a strong foundation. In this episode, we're going to cover several calculations in Excel. To help visualize the tasks we'll be performing, let's now move to a dummy Excel sheet. Now, I'm displaying a dummy Excel sheet on this PowerPoint presentation to illustrate exactly what we're going to cover in this episode. In this sheet, you're looking at some adjustments for a doubly reinforced section, such as the introduction of compression bar diameter, number, and layers, as well as the area of compression steel, ASC. In all the bluish-gray cells, we're going to calculate the following in Excel. Preparation of an automated, interchangeable design heading, singly reinforced or doubly reinforced section. Preparation of the design code. Cover in the compression zone, D. Ratio of D. by DEFF. This ratio will help us find the value of compressive stress of steel, FSC, at the D. level. Area of compression bar, ASC. Calculation for the value of FSC with respect to the ratio of D. by D. Percentage of maximum tensile and compression steel PT max and PC max, as per IS-456. Calculation of required compression steel PC REQ. Calculation of provided compression steel PC PROV. Check for PC REQ and PC PROV. Final check for PT REQ and PT PROV and PC REQ and PC PROV. The parameters, I have already explained in the episode of Excel for IS-456, single reinforced section and steel percentage in Excel Part-02 are effective depth of the beam, DEFF. Area of tension bar provided, ASTPROV. Ratio of the maximum allowable distance of the neutral axis from the extreme fiber of the compression zone to effective depth, XU max by DEFF. Ratio of the maximum limiting moment MU lim and B multiplied by D squared for the beam. Ratio of the design moment MU and B multiplied by D squared for the beam. Ratio of the actual neutral axis from the extreme fiber of the compression zone to effective depth. Percentage of limiting tensile steel PT lim, percentage of required tensile steel PTREQ and percentage of tensile steel provided PTPROV. Check for PTREQ and PTPROV. The list of tasks is quite long, but don't worry. After watching this video, you will be a master of this. It's the beginning of the show, and I hope you will find this tutorial insightful. Your feedback and questions are always welcome in the comments section below. If you found this video beneficial, please like, share, and subscribe. Alright, let's move over to the original Excel sheet now. We're on the actual Excel sheet now. First, I'm going to create a design heading in the merged cells from B1 to G1, which I've named design_1. To do that, I'll select the Excel formula for the heading. For your clear vision of my activity, I've developed a drop-down menu of formulas, and I'm choosing the first one. This is the formula I'll use. Equals to if, open parenthesis, mu, lim by bd square less than mu by bd square, comma, within quotation, 02 doubly reinforced section, comma within quotation, 01 singly reinforced section, close parenthesis. I'll copy and paste this formula into the merged cell B1 to G1. You'll immediately see the heading 01 singly reinforced section. This formula tells Excel, if our calculated mu, lim by bd square is less than mu by bd square, then write 02 doubly reinforced section. Otherwise, write 01 singly reinforced section. Since our calculated mu, lim by bd square is currently greater than mu by bd square, we're seeing 01 singly reinforced section. Now, we need to set up the design type code in cell A1, which I've named design_code. Again, for your clear vision, I'm selecting the Excel formula for this from the drop-down menu, it's the second one. This is the formula. Equals to value open parenthesis, mid open parenthesis, design_01 comma, 2, comma, 1, close parenthesis, close parenthesis. I'll copy and paste this into cell A1. In simple terms, Excel's mid function will select characters from the text, starting from the second character and returning one character. Simultaneously, Excel's value function will convert that text into a number if it is a number. Since our heading will be either 01 singly reinforced section or 02 doubly reinforced section, we'll get a 1 or a 2 as our code. For the present situation, with our heading 01 singly reinforced section, we are seeing 1 as our design type code. Now, I'm going to change the value of mu from 50 kN to 100 kN. See, our code changes from 1 to 2. I need to hide this digit because I think unrelated text or numbers associated with the design heading are unnecessary. To make this heading more informative and attractive, I'll put some conditional formatting on the top row. First, select cells from A1 to H1. Select base color as light pink. Now select cell A1 and choose light pink color for the font. Now select cells from B1 to H1. Go to the Home tab, select Conditional Formatting, and then choose the option Use a formula to determine which cell to format. In the dialog box, type equals to open parenthesis, select cell A1 equals to 1, close parenthesis. Then, select Format, then Fill, and choose green as the fill color. Select OK to accept the conditional formatting. Once again, select cell A1. Go to the Home tab, select Conditional Formatting, select New Rule and then choose the option Format Cells that contain. Under Format Only Cells with Section, select Cell Value in the first dialog box. Then in the second dialog box, select Equals to, then in the third dialog box, type 1. Then click on Format tab, then select Fill, then select the More Colors option. Here select the green color or any color different from the base color, and also select the green as a font color. Our heading is ready. Once again I am changing the value of mu, from 100 kN to 50 kN. See the heading, changes from 02 doubly reinforced section to 01 singly reinforced section and the value of design_code, is also invisible. Now, we're observing a calculation for the analysis for a singly reinforced beam. FCK, 20 Newton per square millimeter, Fy, 415 Newton per square millimeter, clear cover is 25 millimeters, width, B, is 250 millimeters. The overall depth, which we'll call capital D, is 350 millimeters. The ultimate bending moment, mu, is 50 kilonewton-meter. We've determined that 2 layers of 12 millimeters diameter bars, with 3 bars in each layer, are sufficient for this problem. Since we need to calculate the steel required for a doubly reinforced beam, we'll now provide the size, number, and layers for our compression bars. In the cells from D5 to E6, under the heading Compression Bars Combination, we'll input this information. The cells are named as follows. D5 is no_1_com, no means number, 1 means first layer, and com stands for compression. Cell E5 is dia_1_com, where dia means diameter of the bars, 1 means first layer, and com stands for compression. Similarly, D6 is no_2_com, and E6 is dia_2_com. For now, I'm inputting 0 as the cell value in each of these cells. Now, it is the time to put the formula in the cell under the heading D. and DEFF by D. First, it is D. For your clear vision, I'm selecting the formula for D. From the drop-down menu. And the formula is, equals to, if, open parenthesis, design_code equals 1, comma, n.r, comma, co plus 0.5 into max, open parenthesis, dia_1_com, comma, dia_2_com, close parenthesis, close parenthesis. By copying this formula, I am pasting it into the cell under the heading D. The simple meaning of the formula is, if, design_code, equals to 1, That means, for a singly reinforced beam, this parameter is not required. Otherwise, put the value of clear cover, CO, plus half diameter of the maximum bar diameter among layer 1 and 2, from compression bars. Presently we are seeing the N.R, stands for not required, instead of any value under D. Because our beam is a singly reinforced beam. Our next target is to put the formula of D. by D or DEFF under the heading D. by DEFF. From the drop-down menu, I am selecting the formula for D. by DEFF. And the formula is, equals to if, open parenthesis, design underscore code, equals to 1, comma, N.R, comma, round, open parenthesis, D underscore dot by D underscore EFF, comma, 2, close parenthesis, close parenthesis. By copying this formula, I am pasting it into the cell under the heading D. by D. The simple meaning of the formula is, if, design underscore code, equals to 1, that means, for a singly reinforced beam, this parameter is not required. Otherwise, put the rounded value of D underscore dot by D underscore EFF, up to 2 digits. Once again we are seeing the N.R, instead of any value under D. by DEFF. Because our beam is a singly reinforced beam. Now, it is the time to put the formula in the cell under the heading FSC, and the formula is equals to, if, open parenthesis, design underscore code equals 1, comma, within quotation N.R, comma, if, open parenthesis, N, open parenthesis, design underscore code equals to, 2, comma, A underscore SC equals to 0, close parenthesis, comma, within quotation, provide ASC, comma, VLOOKUP, open parenthesis, D underscore dot underscore D underscore EFF, comma, table underscore F, $A $3 F $18, comma, match, open parenthesis, FY, comma, table underscore F, $A $2 F $2, comma, 0 close parenthesis, close parenthesis, close parenthesis, close parenthesis. Now I am pasting this formula to the cell under the heading, FSC. Simple meaning of this formula is, if it is a 0,1 singly reinforced section then value of compressive stress at D. level FSC is not required to calculate. If it is a 0,2 doubly reinforced section and A underscore SC equals 0, then type provide ASC, otherwise find the value of FSC, from table F of sheet F, by the help of VLOOKUP, and match function. Here match function will find the column index for VLOOKUP function depending on the value of Fy. And VLOOKUP function will find the value of FSC, from that column. Here lookup value for VLOOKUP is the value of D underscore dot by D underscore EFF. Presently, we are seeing, under cell FSC is N.R, since it is singly reinforced section. Now I am changing the value of Mu, from 50 kN to 100 kN and we are seeing provide ASC. Since we have not provided any steel in compression bars combination section. Now, I am going to set the formula for provided area of compression steel, beside the cell titled with ASCPROV, and the formula is, equals to if, open parenthesis, design underscore code equals 1, comma, within quotation n.r, comma, 0.25 multiplied by pi, open parenthesis, close parenthesis, multiplied by, open parenthesis, no underscore 1 underscore com multiplied by, square of dia underscore 1 underscore com, plus, no underscore 2 underscore comp multiplied by square of, dia underscore 2 underscore com, close parenthesis, close parenthesis. I think, I need not to explain this formula. I am pasting this formula beside the cell with title, ASCPROV. Since the value of all the compression bars are 0, presently, the value of ASCPROV is 0, I am changing the value of mu, from 100 kN to 50 kN. With this change we are seeing, value of changed from 0, to n.r. I think you already came to know the reason behind this. As I told in my PowerPoint presentation, as per IS-456, maximum tension and compression reinforcement percentages are 4% of the gross area of the cross-section. Now I am typing the number 4 beside the cell with title, PT max and PC max. Percentage of required steel in compression zone, for doubly reinforced section. Now, it's time to put the formula in the cell under the heading PCREQ. The name of the cell is P_C_REQ. And the formula is, PC, REQ equals if, open parenthesis, N, open parenthesis, design underscore code equals 2, comma, A underscore SC equals 0, close parenthesis, comma, provide ASC in quotations, comma. If, open parenthesis, N, open parenthesis, design underscore code equals 2, comma, A underscore SC greater than 0, close parenthesis, comma, open parenthesis, 100, multiplied by, open parenthesis, mu underscore b underscore d underscore 2 minus mu underscore lim underscore b underscore d underscore 2. Close parenthesis. Multiplied by d underscore EFF divided by. Open parenthesis, f underscore sc minus 0.446 multiplied by fck, close parenthesis. Multiplied by open parenthesis d underscore EFF minus d underscore dot. Close parenthesis, close parenthesis, comma, NR. In quotations. Close parenthesis, close parenthesis. Now I'm pasting this formula into the cell under the heading, PCREQ. Understanding the formula's logic. This formula helps us figure out the amount of reinforcement needed in the compression zone for a doubly reinforced concrete section. First, it checks, is the design code 2? If the design code is 2, then it will check if the area of steel in compression, A underscore SC. If A underscore SC equals 0, it tells us, you need to provide the area of steel in compression A underscore SC. This is a critical first step. However, if the design code is 2, and A underscore SC is greater than 0, it will calculate the value for the required area of steel in compression or A underscore SC by following the formula. We know for a doubly reinforced section, mu BD squared will be greater than mu lim BD squared. First, it will calculate the difference between MUBD squared and MULIMBD squared. Then this value will be multiplied by effective depth, D_EFF, and divided by the difference between F_SC and 0.446 multiplied by FCK, multiplied by the difference between effective depth, D_EFF, and D_dot. The entire term will then be multiplied by 100. Finally, if the design code is 1, that is, for a singly reinforced section, then the formula simply says N.R, which means not required. Since the present calculation based on singly reinforced section, we are seeing N.R. Excel formula for the calculation of the percentage of provided compression steel for a doubly reinforced section, or PCPROV. Now, I'm going to place the formula in the cell under the heading PCPROV. The name of the cell is P_C_Pro. And the formula is, equals if, open parenthesis, design_code equals 1, comma, NR. In quotations, comma, if, open parenthesis, and, open parenthesis, design_code equals 2, comma, A_SC equals 0, close parenthesis, comma, within quotation, provide ASC, comma, open parenthesis, 100 multiplied by A_SC, close parenthesis, divided by, open parenthesis, B multiplied by D_EFF, close parenthesis, close parenthesis, close parenthesis. Now I'm pasting this formula into the cell under the heading, PCPROV. This formula tells us, if the design code is 1, we don't require this calculation. If the design code equals 2 and A_SC equals 0, then it will say provide some compression steel, or provide ASC. Otherwise, it will calculate the value of the percentage of provided compression steel, or PCPROV, using this formula, 100 multiplied by A_SC, divided by B multiplied by D_EFF. Since the present section is a singly reinforced section, we are seeing N.R, which means not required. Checking for the percentage of compression steel required P_C_REQ and percentage of compression steel provided P_C_Pro. On the cell under the heading check for PC, I'm going to put this formula to check the percentage of compression steel required and provided. The name of this cell is check_02. And the formula is, equals if, open parenthesis, design_code equals 1, comma, NR. In quotations, comma, if, open parenthesis, and, open parenthesis, design_code equals 2, comma, A_SC equals 0, close parenthesis, comma, in quotation, provide ASC, comma, if, open parenthesis, and, open parenthesis, design_code equals 2, comma, P_C_Pro greater than or equal to, P_C_REQ, comma P_C_Pro, less than or equal to, PT_max_PC_max, close parenthesis, comma, in quotations, O.K, comma, check, in quotations, close parenthesis, close parenthesis, close parenthesis. Now I'm pasting this formula into the cell under the heading, check for PC. Since the present section is a singly reinforced section, we are seeing N.R, which means not required. Understanding the formula's logic in simple words. This formula helps us quickly check if the amount of compression steel we've provided, P_C_Pro, is appropriate compared to what's required, P_C_REQ. Here's how it works. First, it checks the design code. If the design code is 1, meaning it's a singly reinforced section, the formula simply says NR. Not required. This check isn't needed for single reinforced sections. If the design code is 2, meaning it's a doubly reinforced section, it then checks for a special condition. If the area of steel in compression, A_SC, is 0, the formula tells you, provide ASC. This means you need to add some compression steel. If the design code is 2 and you have provided some A_SC, the formula performs the main check. It looks at 3 things. Is the design code still 2? Is the provided percentage of compression steel, P_C_Pro, greater than or equal to the required percentage of compression steel, P_C_REQ? We want to make sure we've put in enough. Is the provided percentage of compression steel, P_C_Pro, less than or equal to the maximum allowed percentage of compression steel, PT_max_PC_max? We don't want to put in too much. If all 3 of these conditions are true, the formula will display O.K, meaning everything looks good. If any of these conditions are false, the formula will display check, telling you to review your design. This formula provides a quick and clear status on whether your compression steel design meets the necessary criteria. Final check, formula for the final check, is equals to if, open parenthesis, or, open parenthesis, and, open parenthesis, design_code equals 1, comma, check_01 equals to O.K, comma, and, open parenthesis, design_code equals 2, comma, check_01 equals to O.K, comma, check_02 equals to O.K, close parenthesis, comma, O.K, comma, check, close parenthesis. Now I'm pasting this formula into the cell under the heading, Final Check. Since the present section is a singly reinforced section, and design is OK, we are seeing O.K. Final Check will check, both singly and doubly reinforced section. Name of this cell is check_03. For singly reinforced section, it will check the check_01. If check_01 it is O.K, it will say O.K. For doubly reinforced section, it will check both check_01, check_02. If both the checks are O.K, then it will say, OK. Otherwise it will say check. We've now completed our task with this final check, but I've also made a few adjustments to our formulas for PT, REQ, and PT, PROV. In our single reinforced beam series, we previously covered PT, REQ, PT, PROV, and how to check for PT. Now that we're integrating doubly reinforced beam design onto the same sheet as our single reinforced beam design, we need to update these 3 formulas. Here are the adjustments. First, formula for PT REQ, The formula for PTREQ equals to, if, open parenthesis, A_ST equals 0, comma, provide AST in quotation, comma, if, open parenthesis, design_code equals 1, comma, round, open parenthesis, 100 multiplied by mu_b_d_2 divided by, open parenthesis, 0.87 multiplied by phi multiplied by, open parenthesis, 1 minus 0.416 multiplied by xu_d, close parenthesis, comma 3, close parenthesis, comma pt_lim, plus, round, open parenthesis, 100 multiplied by, open parenthesis, mu_b_d_2 minus mu_lim_b_d_2, close parenthesis, divided by, open parenthesis, 0.87 multiplied by phi multiplied by, 1 minus 0.416 multiplied by xu_d, close parenthesis, comma, 3, close parenthesis. Simple meaning of PTREQ formula. This formula, PTREQ, calculates the percentage of steel reinforcement that's actually required in the tension zone of our concrete beam. First, it checks if you have any steel. If the area of steel in tension, A_ST, is 0, it immediately tells you, provide AST. You can't have a concrete beam without tension steel. If you do have tension steel, it then checks the design code. If the design code is 1, meaning it's a singly reinforced section, it calculates the required percentage of tension steel. This calculation involves the ultimate moment of resistance, mu_b_d_2, material strengths, phi, and effective depth, adjusted for the neutral axis depth, su_d. It also rounds the result to 3 decimal places. If the design code is not 1, meaning it's a doubly reinforced section, it uses a more complex calculation. It takes the pt_lim value, which is for the balanced single reinforced section, and adds an additional percentage. This added percentage accounts for the extra moment carried by the doubly reinforced section. This additional calculation also uses material strengths, the ultimate moment of resistance, and the limiting moment of resistance, mu_lim_b_d_2. The result is also rounded to 3 decimal places. In short, this formula figures out the minimum percentage of tension steel you must have based on your beam's design and how much load it needs to carry. Now, the formula for PTPROV equals if, open parenthesis, A_ST equals 0, comma, provide AST, comma, open parenthesis if, open parenthesis, 100 multiplied by A_ST, divided by, open parenthesis, B multiplied by D_EFF, close parenthesis. Simple meaning of PTPROV formula. This formula, PTPROV, calculates the percentage of steel reinforcement that you have actually provided in the tension zone of your concrete beam. Here's how it works. First, it checks if you have any steel. Just like the previous formula, if the area of steel in tension, A_ST is 0, it tells you, provide AST. If you do have tension steel, it then checks a special condition. It calculates the actual percentage of steel you've provided. It takes 100 multiplied by the area of steel in tension, A_ST, and then divides that by the width of the beam, B, multiplied by the effective depth, D_EFF. Essentially, this formula gives you a clear number for how much tension steel you've actually put into your beam, in percentage form. Adjustment for, check for PT, the formula for check for PT is, equals if, open parenthesis. If A_ST equals 0, comma, then provide AST in quotations, comma. If, open parenthesis, N, open parenthesis. If design code equals 1, comma, and PT provided is greater than or equal to PT required, comma, and PT provided is less than or equal to PT limit, comma, and PT provided is greater than or equal to PT required again, comma, and PT provided is less than or equal to PT max PC max, close parenthesis, comma, then OK in quotations, comma. If, open parenthesis, N, open parenthesis. If design code equals 2, comma, and PT provided is greater than or equal to PT required, comma, and PT provided is less than or equal to PT max PC max, close parenthesis, comma, then OK in quotations, comma. Otherwise, check, in quotations, close parenthesis, close parenthesis, close parenthesis. In simple terms, this formula helps us verify the amount of tensile steel, or PT, provided in a concrete section. First, it checks, have we provided any steel for the tension zone at all? If AST is 0, meaning no tensile steel is provided, it will tell you to provide AST. However, if some tensile steel is provided, the formula then does another check based on your design code. If your design code is 1, it confirms several things. Is the provided tensile steel both greater than or equal to the required tensile steel and less than or equal to the tensile steel limit? Additionally, it checks again if the provided tensile steel is greater than or equal to the required tensile steel and less than or equal to the maximum permitted tensile steel. If all these conditions are met, it will say OK. If your design code is 2, it checks 2 conditions. Is the provided tensile steel both greater than or equal to the required tensile steel and less than or equal to the maximum permitted tensile steel? If both conditions are met, it will say OK. If any of these conditions are not met for either design code, the formula will alert you with check, indicating that something needs to be reviewed in your design. Let's set up conditional cell formatting for our final check column. First, select the cells under the final check heading. Next, click on the Home tab on the ribbon. Then, navigate to the Conditional Formatting tab and select the New Rule option. After selecting New Rule, from the panel of menus, choose Format Only Cells that contain. Now, in the Format Only Cells with section, from the first drop-down, select Specific Text. From the second drop-down, select Containing. Finally, type OK without any quotation marks. Then, go to the Format button, select the Fill tab, and choose green as the color. Green is our universal symbol that everything is OK. To accept this conditional format, click OK twice. Now, one more step, go back to the Home tab and use the Fill Color option to fill these same cells with yellow. This yellow fill will automatically appear when a cell doesn't contain the text O.K, serving as a reminder that our design isn't finalized yet. Testing for singly reinforced beam section. We have now completed all the tasks to develop this dynamically interchangeable design Excel sheet for both singly and doubly reinforced sections. This sheet is designed to accurately account for bending stresses in both the tension and compression zones of a beam. It's time to put our design to the test. Test number 1. Initial setup and deletion test. Presently, our beam's overall depth is 350 mm, and its width is 250 mm. The ultimate bending moment, MU, is 50 kN. We are using M20 grade concrete and Fe415 grade steel, with 3 16 mm diameter reinforcing bars. In this specific scenario, our design is confirmed as OK. Now, observe as I delete the reinforcing bars. Notice the status under the headings PT Lim, PT REQ, PT PROV, and check for PT. We now see the prompt provide AST. This indicates that our current steel provision is insufficient for the required moment. By using the undo option, I will return to our initial, OK design configuration. Effect of changing grade of concrete for singly reinforced beam section. Test number 2, concrete grade variation. Next, I am changing the grade of concrete from M20 to M15. While M15 grade concrete is generally not recommended for new construction, it can be crucial for assessing existing structures during retrofitting or repair projects. With this change, we observe several modifications in our design parameters. PT Lim changes from 0.955% to 0.716%. This decrease is expected, as lower strength concrete has a lower limiting strain and thus a lower capacity before crushing. PT REQ changes from 0.655% to 0.699%. Additionally, the cells for PT REQ, PT PROV, check for PT, and final check have turned yellow, indicating a warning. Here, PT PROV is now higher than PT Lim, meaning our section has become over-reinforced. We must readjust our tensile reinforcement. To rectify this, I am now changing our bar combination from 3 16 mm diameter bars to 5 12 mm diameter bars, arranged in 2 layers. Notice once again, the status of our design is now OK. This demonstrates how crucial it is to maintain an under-reinforced section for ductile behavior. Now, let's explore further by changing the grade of concrete from M15 to M25, M30, and M35. Observe how PT Lim and PT REQ respond. As we increase the concrete grade, PT Lim will generally increase, reflecting the concrete's higher compressive strength, while PT REQ will decrease marginally as the section becomes more efficient. Changing from M15 to M25, PT Lim increases from 0.716% to 1.194%, and PT REQ changes from 0.699% to 0.631%. The design remains OK. Now, I am changing the bar combination back from 5 12mm diameter bars in 2 layers to 3 16mm diameter bars in a single layer. Changing from M25 to M30, PT lim increases from 1.194% to 1.433%, and PT REQ changes from 0.631% to 0.616%. Changing from M30 to M35, PT lim increases from 1.433% to 1.672%, and PT REQ changes from 0.616% to 0.606%. Accordingly, we must continuously adjust our singly reinforced design to ensure both safety and efficiency with varying concrete grades. Test number 3, Effect of changing grade of steel for singly reinforced beam section. Now, I am changing the grade of steel from Fe415 to Fe250. As a result, the fill color of the cell under the heading Phi turns yellow. The reason is similar to the M15 concrete case. The properties of the material have changed significantly, affecting the design's balance. By keeping the concrete grade at M35, and changing the steel grade from Fe415 to Fe250, PT lim changes from 1.672% to a much higher 3.706%. This is because Fe250 steel yields at a lower stress, allowing for a deeper neutral axis before concrete crushes, hence a higher limiting steel percentage. PT REQ changes from 0.606% to 0.968%. As a result, the current design is no longer okay. To rectify this, I am adding 2 12mm diameter bars in the second layer. With this adjustment, our design is now okay. Next, I am changing the steel grade from Fe250 to Fe500. PT lim changes from 3.706% to 1.321%. PT REQ changes from 0.968% to 0.541%. The design is currently okay. Now, I am deleting the 2 12mm diameter bars from the second layer and changing the primary reinforcement from 3 16mm diameter bars to 4 12mm diameter bars. With these changes, the design is still okay. Finally, I am changing the steel grade from Fe500 to Fe550. PT lim changes from 1.321% to 1.167%. PT REQ changes from 0.541% to 0.473%. The design is currently okay. And lastly, changing the grade from Fe550 to Fe600. PT lim changes from 1.167% to 1.043%. PT REQ changes from 0.473% to 0.417%. Once again, the design is okay. This demonstrates how critical the interplay between concrete and steel grades is in achieving an efficient and safe singly reinforced beam design, constantly requiring adjustment of the reinforcement. Test number 1, Initial Setup and Observation. Now we are seeing M35, grade of concrete, Fe600, grade of steel, 5 numbers of 12 dia bars as 8 iron bar in 2 layers. Now, it's time for testing our doubly reinforced beam section. For test number 1, I'm returning to our starting point by changing the concrete grade from M35 to M20 and the steel grade from Fe600 to Fe415. I'm also changing the tension bars combination from 5 number 12 diameter bars to 3 number 16 diameter bars. Currently, as a singly reinforced section, our design is okay. For the time being, I'm not providing any bars in the compression bars combination. I'm changing the ultimate moment MU from 50 to 150 kN, while keeping other parameters like overall depth and width the same as before. As a result of these changes, we observe that the heading of our design has dynamically adjusted to 02 doubly reinforced section from 01 singly reinforced section. Also, we see check. Under the cell heading check for PT. Under the cell headings PC, REQ, PC, PROV, and check for PC, it says provide ASC as a reminder. And finally, in the final check cell, it shows check. Test number 2, adjustment in initial setup and deletion test. Moving on to test number 2, look at this calculation. The value of PT, REQ is 2.065%, but PT, PROV is only 0.761%. This means we provided less steel than required. Now, I'm changing the diameter of the tension bars from 16 to 25 millimeters. In the first layer, with this change, the design steel for tension is not okay. For further adjustment, I'm providing the number 2 numbers of 12 dia bars in the second layer. Observe that our design is okay, and the difference between PT, REQ, and PT, PROV has become even narrower. Test number 3, clarification regarding doubly reinforced beam section. For test number 3, let's consider a scenario where we're free to increase our beam's depth, width, or both. Since increasing the depth is generally more effective in resisting bending moment or bending stress, I'm now changing the depth from 350 to 550 millimeters. Notice how the title of the design changes from 02 doubly reinforced beam section to 01 singly reinforced beam section. Now, I'm changing the bar diameter from 25 mm to 16 mm, without altering the number of bars. We can see the design is now okay. This brings us to an important question: why and when should we opt for a doubly reinforced section? The simple reason for adopting a doubly reinforced section is the confinement of the beam's dimensions. I've explained this clearly in the first part of this video series. Test number 4, design of the beam as a doubly reinforced beam section. Finally, test number 4. First, I'm returning to our initial position by changing the beam's depth from 550 back to 350 millimeters and the bar diameter from 16 back to 25 millimeters. I'm also providing some compression steel under the compression bars combination section. Let's say it's 3 number 16 diameter bars in one layer. With the introduction of the steel, we observe a value under the cell heading FSC, which is 351 newtons per square millimeter. FSC represents the compressive stress in the steel at the D dot level within the compression zone. The value of FSC will change with alterations in the D dot by D ratio and the grade of steel. The D dot by D ratio changes when we adjust the clear cover and the maximum diameter of the bar used in the compression zone. Generally, we don't change the clear cover, but sometimes we need to change the bar diameter. To maximize the advantage of FSC, we should use bars with smaller dimensions. To demonstrate this, I'm now changing the bar diameter from 16 to 25 millimeters. Observe the values of FSC. The value of FSC changes from 351 newtons per square millimeter to 349 newtons per square millimeter. To get the maximum advantage from FSC, bars with lower diameter is preferable. After using the three numbers of 25 dia bars, we are seeing PC, PROV, is greater than PC, REQ. And the design is okay. To narrowing the gap between PC, PROV, and PC, REQ, I am changing the bar dia from 25 millimeters to 20 millimeters. Still our design is okay. And value of PC, PROV, is 1.206%. Once again, I am changing bar dia from 3 numbers of 20 millimeters dia bars to 5 numbers of 16 millimeters dia bars in 2-layer. Design is still okay. And value of PC, PROV, is 1.287%, which is greater than 1.206%. So, we must stick on 3 numbers of 20 millimeters dia bars for our design. Here, I must add something. To my knowledge, in Table F, you'll typically find the value of FSC for a maximum steel grade of 500 newtons per square millimeter. Gemini AI helped me develop this extended table for steel grades up to 600 newtons per square millimeter. A big thank you to Gemini AI. If you have any information or references regarding this, please share them with me. In our current situation, the design for both tension and compression are okay, hence, the final check is also okay. Believe me, I'm really on a roll here, and my heart is absolutely bursting with more to share. But, I'm mindful of your time, and I want to make sure you get the most out of each session. So, I'll reluctantly pause here for now. And that brings us to the end of Doubly Reinforced Beam Design for Bending Stress in Excel, Part-02. Today, I explained in detail the doubly reinforced beam and bending stress on our Excel spreadsheet, and I'm going to be taking a brief break to prepare for Part-03. In the next video, you'll see the explanation regarding shear stress and deflection limits, along with the final check for the doubly reinforced beam. Now, for a quick announcement about something many of you have been asking for, the free Excel sheet that I've already demonstrated. I've received so many wonderful emails requesting it, and I'm truly happy to share it with you. To get your hands on it, please carefully read the instructions in the description below this video. It's a 2-step process. You'll need to send an email with your request and leave a comment on this specific video letting me know you've sent it. Both steps are absolutely essential. Once you receive the file, a quick "got it" or "thank you" in the comments would truly mean a lot to me. However, for this particular beam designing series, since it's genuinely a do-it-yourself project, I truly encourage you to try developing your own Excel sheet first. This is, in fact, my primary objective behind creating these types of videos. The flexibility of pre-made third-hand sheets is often limited, so developing your own will truly empower you. I deeply believe in the power of curiosity. The phrase "I don't know" is often the common starting point for truly wise individuals, those willing to explore and discover something special. It holds immense opportunity. We often make the mistake of thinking someone who says "I don't know" is a fool. But let's complete that thought: I don't know, but I want to know. That's where true growth begins. If you encounter any problems at all while developing your sheet, please know that I'm ready to assist you, completely free of cost. My goal is to empower you to learn and build your skills. If for any reason you hesitate to take this free assistance, and you feel moved to contribute, you can make a contribution, whatever your pocket permits, without any burden or pressure. The communication process for that will be the same as for the Excel sheet request. To support me, you'll find the support details in the description. This communication process helps me understand how engaged you all are and allows me to refine how I share this knowledge with you. I truly hope you enjoyed this episode. Your feedback and questions are always welcome in the comments below. If you found this video helpful, please do give it a big thumbs up, share it with your colleagues and friends who might benefit, and most importantly, don't forget to subscribe for more valuable content like this. Thank you so much for your cooperation and support.